Hello, my name is Natasha Anak Jayong.
Hi, my name is Viviana JC.
Hey, my name is Narma.
Hello, my name is Fu Leong-Ling.
Hello everyone, my name is Erin Lat.
To begin the DNS assay, we first prepare 6 clean and dry test tubes. Each test tube will contain different volumes of the sample and distilled water as shown in the table. In test tube 1, we add 1000 microliters of the sample and no distilled water. In test tube 2, we mix 500 microliters of the sample and 500 microliters of distilled water. Test tube 3 contains 250 microliters of the sample and 750 microliters of water, while test tube 4 contains 100 microliters of the sample and 900 microliters of water. Test tube 5 has only 50 microliters of sample diluted with 950 microliters of distilled water. And finally, test tube 6, the blank, contains 1000 microliters of distilled water only with no sample added. Next, we add 1 milliliter of DNS reagent to each of the test tubes regardless of the sample volume. Once all the reagents have been added, we boil the test tubes for 5 to 7 minutes to allow the DNS reagent to react with any reducing sugars present in the samples. After boiling, we let the test tubes to cool down at room temperature. Once cooled, we add 1 milliliter of Rochelle's salt solution to each test tube. This helps to stabilize the color complex formed during the reaction. Finally, we measure the color intensity of each mixture using a spectrophotometer at 575 nanometers. The absorbance reading reflects the concentration of reducing sugars in each sample. Test tube 6 serves as the blank to eliminate background interference since it contains no sample but only the distilled water and reagents. In this part of the video, I will be interpreting the results obtained from the DNS assay for glucose quantification. Let's start with table 1. This shows the absorbance values recorded at 575 nanometers for different volumes of the unknown drinking sample. We tested in total of 5 dilutions ranging from 1000 microliters down to 50 microliters and measured the absorbance in duplicates as well. As expected, the absorbance values decreased with smaller sample volumes, which makes sense because less volume means less reducing sugar is present in the reaction mixture, resulting in less formation of the reddish-brown chromophore. The blank, which contained only the reagent and distilled water, recorded an absorbance of 0.000, confirming that there was no background interference in the reaction. Now moving on to the table 2, we use the average absorbance values from table 1 to determine the glucose concentration of the drink sample. This was done using the equation of the standard curve obtained earlier, which was y equals to 0.9575x plus 0.0209. The values in the glucose concentration column represent the estimated glucose levels based on the calibration curve. Then using the known dilution factor for each sample, we calculated the actual glucose concentration after dilution, which is shown in the last column. As you can see, there is a clear increasing trend. The most diluted sample, 200-fold dilution, had a final concentration of about 202.6 gram per liters, while the least diluted sample, which was about 10-fold dilution, had about 14.02 grams per liter. This trend supports the idea that more diluted the sample, the higher the original concentration, because we needed to dilute it more to bring it within the detectable range of the assay. Overall, the data confirms that the DNS method is effective in determining reducing sugar content, and the drink sample we tested contains a high amount of glucose, especially in the less diluted portions. The full calculation for all values shown here, including how we applied the calibration curve and calculated dilution effects, are provided in the written report for reference.